Okay, so we're going to start out Unit 6 by graphing exponential functions. And graphing exponential functions is something we have never done before. We've graphed linear functions, and that's all we've graphed so far. And we're going to eventually get into quadratic functions. So there's something called the function family, and all of the graphs look differently. And as of right now, the only graph that you are used to seeing is a straight line. Okay, and that comes from the linear family. So let's take a look at what it means for a graph to be linear. Okay, so in Unit 4 and 5, you got lots of practice with linear functions. So hopefully you know them pretty well by now. A linear function would look something like this. -1, 2, 5, and 8. All right. So if I asked you to write a rule for this function, which was in Chapter 4 somewhere, or Unit 4 somewhere, you said to yourself, well, it's going up by ones. So for every one that this is going up, okay, and it was really helpful to put this, you saw that this was going up by 3. All right, so we called this our constant rate of change. So for every one it goes up, this goes up by 3. So you knew right away that your slope or your rate of change was 3. And then we looked at our y-intercept and we said, where does this function begin? And you knew that it was wherever x was 0, the corresponding y value is what gave you your beginning value. So your y-intercept was 2, and then you created a graph of that. Y equals, and then you just kind of filled those in, right? You said y equals 3x plus 2. Okay? So that's linear. That's what we're used to seeing. So let's take a look at what exponential is going to look like. So an exponential function will have a table that looks like this. We're going to stick with these 5 points for the duration of this learning target. It's just going to be an easier way to keep track of them. So we're going to look at this. I'm going to put some crazy numbers here, so just kind of be careful for a second and don't get too freaked out. It's not going to be so bad. Okay? This is, I will say this, you can kind of tell right off the bat, this is going to be a set of notes that you're really, really going to have to pay close attention to. It may be even a set of notes that you have to watch a couple times because there are a lot of little pieces to this puzzle that you need to make sure you fit them in correctly. And once it clicks, it'll be really easy, but kind of figuring out what belongs where and what controls what is going to really take some concentration on your part. So stay with me here. Okay, so first thing we want to do is kind of say, well, if I were to ignore those 2 points right there, because those are our negatives and our fractions. Those are ones that we really don't want to have to deal with. So let's ignore those for right now. Okay, and let's just see if we can find a pattern going from this way forward. So the good news is we're going up by ones. Okay, and every time that goes up by ones, the rate of change in your y values is going to be that rate of change. But if I approach this the way I approached looking at my linear function, you're going to really have a hard time because you're seeing that it went up from, first it went up 4, then it went up 12, and you're not going to be happy with that because it's nothing we've seen before. So I'm going to ask you to look at it differently. Instead of going up by 3, meaning I kept adding 3, can you see something else that I did? 2 to get to 6. 6 to get to 18. It's totally different than what we've done before. Instead of adding 3, I'm multiplying by 3. 2 times 3 is 6. 6 times 3 is 18. The next point would be 18 times 3. So we are not adding a constant anymore. We are multiplying, okay? So then I guess what you could do is we could just kind of say, well, this is still going up by 1. Let's just double check this to make sure that this is right. Let's just see if I went from 2/9. Did I multiply by 3 to get 2/3? From 2/3 to 2, did I multiply by 3 to get that? So let's just check it out. Let's go off to the side here, and let's take 2/9 and see if I multiplied by 3 to get that. So 2/9, oops, that's why it didn't work, because that's not supposed to be. So let's take a look at this here. Did I multiply 2/9 by 3 to get 2/3? Yes, that works, because if you don't want to cross cancel, that would be 6/9, but we do cross cancel, and there's your 2/3, right? So now let's see if 2/3 times 3 is 2. 2/3 times 3 is 2, and it is. So these kind of fractions right here throw us off maybe a little to begin with, but if you're just seeing that instead of plus 3, plus 3, plus 3, it's times 3, times 3, times 3, that's what defines an exponential function. So next we want to take a look at one other thing. So what we have, we use this information here to put it into a nice, neat little equation. So what we need to do next is use that to put this into a nice, neat little thing here. So we started out with y equaled mx plus b, right? So we did y equaled mx, and then we had our plus b. Okay, we're going to have a similar situation to that, okay? Don't really like that that's a b there, but let's just take a look at what this is. Your exponential function looks like this. Y equals ab to the x power, okay? And oh man, this being a b right here, I kind of need you to not make that connection because it's being used for something different here. So if I were to graph that, I'm still looking at this point right here. Okay, so see how it was 0, 2 here, and it was 0, 2 here, and this was plus 3, and this is times 3. Let me just kind of show you where this fits in. This y is going to stay, and this x is going to stay. It's the a times the b that it's going to do right here. Here's the tricky part about this. This 3 was the green one up here, and it belonged with the x. This green 3 also belongs with the x. So I want you to look at this. This is going to be y equals not 3x like it was up here, but 3 to the x. Okay? So make that transition. The number that's being multiplied as a constant multiplier is still with the x, but it's the base for the x. So instead of 3x, it's 3 to the x. Got it? So then what does that mean for this right here? This, when x is 0, whatever number is with the y, that's going to be the a. Okay? So the answer to this graph right here of this exponential function is y equals 2 times 3 to the x. All right, so what we want to see now is what is this going to look like? And I had you guys watch 2 preview videos, so you kind of should. You watched a 7-minute video, hopefully, and a quick 5-minute video. So you should kind of know what exponential functions look like. They're not linear. So exponential functions are non-linear. Means it's not going to be a straight line. So for the first time we're looking at a graph that's not a straight line. Okay, we're going to see it again in Unit 8, but in Unit 6 we're seeing for the first time something nonlinear. So instead of graphing from here, let's graph using our points. Let's always start with this. So let's do our 0, 2 is right here. Our 1, 6 would be right here. And then our 2, 18. Well, holy cow. That got big fast, didn't it? So if this is 1, 6, 2, 18 is somewhere up here, okay? So I have this part of it, and I know you're going to be tempted to want to connect it and have it be a straight line, and I know it looks like it's a straight line. Let's get these negative ones in. Let's do -1 2/3, and holy cow, because of the way I made my increment so small, it's going to look really tiny. So I'm going to go -1 2/3. Then I'm going to go -2, +2/9, which is even smaller, which means it's even closer to the x-axis. And this just kind of swoops down here like that. And here's what's going to happen. The more I get smaller on this x-axis, the closer this graph is going to get to the x-axis. But in that preview video, remember what the guy said? It's never going to actually touch it. It's just going to keep getting closer and closer. And obviously we can't tell by this graph because I have a thick pen and I hand wrote the graph. This is actually never going to touch. So an exponential function looks like this. And that's the definition of what exponents are. They get really, really big, really, really fast, okay? So that kind of gives you an idea of what exponential functions look like. So what I want to focus on next is going to talk about the difference between exponential growth versus exponential decay. So let's take a look at that. So growth versus decay, okay? So this is exponential growth. Growth is exactly what it sounds like. Something grows exponentially. That would be like increasing your savings by not $1 a day. That would be linear. Linear would be on day 1 I had 1, on day 2 I had 2. Exponential growth would be I'm increasing it by a certain percentage per day. So I'm increasing it based on the previous percent, which means it's going to get big fast, okay? Exponential decay is going to mean it's going to get small fast, okay? So it's going to decrease. So let's talk about, in both of these, we still have our AB to the x, okay? And also know that if it's written in function form, it could be f of x equals AB to the x. It could be g of x. It could be h of x. It could be whatever we want it to be. So know that y, and we learned that in Unit 3, right? That f of x and that g of x are really interchangeable, right? Okay? So taking a look at growth versus decay, a couple parameters have to be in place first. And for both of them, the a has to be greater than 0 for it to work, okay? And we're going to talk about the b next. The b then, which is that base there, for growth to happen, this value that I put to the x power has to be greater than 1. All right? And for it to be a decay, we're going to talk about decay in my second video, so we're not going to focus on it right now. For you to have decay, your b has to be between 0 and 1. That's a fancy way of saying b is greater than 0, but less than 1. It can't be 1, and it can't be 0. It can be all those numbers in between. So basically what I mean when I write this is a proper fraction. I'm talking about all those numbers in between. So basically I'm talking about b can be a proper positive fraction. Okay, we're going to spend some more time on this on our next video. So for right now, let's just talk about exponential growth. Growth meaning that the b, the base, is greater than 1. For example, y is equal to 4 to the x. Y is equal to 2 to the x. Y could be equal to 100 to the x. And in the video that I keep referring to, the preview video, you kind of saw a little idea of what that did. The bigger the coefficient, the quicker that was growing. So 4 to the x, 2 to the x power grows pretty quickly, but something that grows 4 to the x power grows even faster than that. And something that grows 100 to the x power grows insanely quick. Okay? So let's kind of take a look at, actually I'll show you this over here. So what I mean by a proper fraction would be y equals not 4 or 2 or 100, but like a 1/3 to the x. Or f of x could equal 2/5 to the x. Or g of x could equal 1/4 to the x. Growth versus decay. Okay, and while I'm here, I may as well just give you a visual and reminder because the guy did anyway. So on those preview notes, growth means it's going to go like this. Decay means it's going to start over here and go like this. Never, ever officially touching either of those axes. And if it doesn't touch that axis, it's never going to go below it either. So all of our exponential functions, at least that we're going to talk about today, are going to take place in quadrants 1 and 2. Okay, we'll talk later about what gets it down here, what flips it and does all that, reflects it and stuff. Okay, so this is a positive coefficient or a whole number greater than 1, growth. I don't want to say less than 1 because less than 1 could mean negative. So we have to say between 0 and 1, it's going to look like this. So let's focus on growth for right now. So let's create some tables of values. And here's the most awesome thing about being given any function. If I were to ask you to do like graph y equals 4 to the x, then you may not know what that looks like right away. If I were to ask you to graph y equals 3x plus 2, yeah, boom, you got it. Start at the y-intercept at 2, and the rate of change is up 3 over 1, and I got that graph down in a matter of minutes. That's because you mastered linear functions. But if you forgot how to graph linear functions, your fallback is always to make a table of values. Meaning, if I chose these 5 points, which are the 5 points we're going to choose, all you have to do is put this in for x and solve it for y. So 3 times negative 2 is negative 6, and negative 6 plus 2 is negative 4. 3 times negative 1 is negative 3, so this is negative 1. 3 times 0, that's going to be 2. And at some point, maybe you remembered, oh, if this is going up by 1s, I kind of see a pattern here. This went up 3. This went up 3. I'm not even going to do that substitution anymore. I'm just going to make it go up 3 again, and that's going to be 5. Then I'm going to make it go up 3 again and make that 8. That's the definition of linear. It's a constant rate of change, right? So when I graph this, there's my 0, 2, right? Right there that you knew it. So what I'm trying to get you to understand is a table of values is your fallback every single time. If I ask you to graph that, you may look at me like, Miss Z, you're crazy. I don't know how to graph that. Yes, you do. Make a table of values and graph it, okay? So before we make that table of values, I have to kind of do something with you real quick. So we need to do a quick review of negative exponents. All right, and by review, I mean there was a quick blurb on it in the intro video. We're not going to really get to negative exponents until 6.3, I believe, but you need a quick knowledge of it before you can even start this lesson. So the first rule is about negative exponents, they're a no-no. You can't have them. You can't have a negative exponent. You need to make them positive. For example, if I had 2 to the negative 1 power, I have to make that negative 1 positive. So to do that, I kind of create a fraction from it, and that meaning this 2 to the negative 1 power is in my numerator. So let's take this and move it down to the denominator, and that leaves me with a 1 up top because you can't have anything left. Remember the guy in the notes? He actually put a times 1 there, which is a great reminder then that you can't just leave it. You have to have that numerator there. And now this is 2 to the positive first power, which is that. Another example could be 3 to the negative 2 power is the same as 1 over 3 to the positive 2 power. So that's 1/9. So remember that? If the negative exponent started in the denominator, then it needs to move to the numerator, which would be 3 to the positive third power, which is the same as 3 times 3 times 3, which is 27. Got it? The other thing to keep in mind is that you will have 5 times 2 to the negative third, right? So 5 times 2 to the negative third, this one's a little trickier because the only thing that needs to move is the negative exponent and its base, right? So that 5 is going to stay put. I'm only moving that 2, which means the 5 stays, and this 2 to the positive third power means 5 over 2 times 2 times 2, which is not 6. It's 8, okay? So why am I showing you all this? Because you're going to need to know how to do all of this when we work on our exponential growth and our exponential decay. So let's move on to exponential growth.